Hello everyone, I'm Caihua Li. Today I will introduce Blindfold, confidential memory management by untrusted operating system. Green one. Okay. So traditional operating system like Linux is not trustworthy because it has a complex code base and a large attack surface. And the complex operating system is typically written in the unsafe languages like C, and also it is usually not certified. And as a result, once the operating system is compromised, the attacker can easily steal the application data like your password and key stored in the memory in the same way as the OS. We noticed that the fundamental reason for this problem is because the operating system has more access capability than it needs. One fundamental job of the operating system is to manage hardware resources like CPU and memory. To fulfill its job, the operating system requires the access to the hardware resources, like accessing the physical memory frame and the CPU register. However, the operating system do not really care about the value, the exact value stored in the resources. Like, for example, when the operating system moving pages, actually it just copy the pages from one frame to another frame without carrying the exact value in the frame, right? So, keeping this in mind, we raise research questions. There is whether the operating system can manage memory without access. To answer these questions, it requires to have a deeper understanding of the operating system. We observe that the Linux requires only non-semantic access to user space for memory management. Here, non-semantic access means the operating system does not really care about the value of the data for management. For example, the paging and the page migration and like the write system call, all these are the typical example of the non-semantic access because OS does not care about the value. Right? It just moves the data from somewhere to another. In contrast, the operating system still needs the value of the data to fulfill its job in the semantic access. Typical example include like the system call parameter stored in the memory, like in the open system call, the parameter pass name, it is stored in the memory, right? And another example is that like in the signal handling. So in this figure on the left, in the figure, we can clearly see that the traditional operating system directly accesses the user space, no matter for the semantic or non-semantic access. It is efficient but insecure because once the operating system is compromised, the attacker can access the entire user space in the same way as the operating system. To address this problem, some previous work always provide the encrypted view to the operating system, or it completely hides the user's sensitive pages from the operating system. Of course, it is secure, right? Because operating system can no longer access the data. However, it is inefficient because the encryption is super expensive, or the operating system optimization will stop functioning because it has no access to the pages being hidden. Right? On the other hand, to support the semantic access, the previous work always copy the system call parameters to a dedicated buffer. As a result, it requires the case-by-case handling for signal handling or some complex system call like filters. And obviously, the case-by-case handling logic will lead to a complex TCP. Right? So after reviewing how traditional operating system and previous work support semantic and non-semantic access. In the following, I will start to introduce the two key design components in Blindfold. In Blindfold, the operating system accesses user space data in a very different way compared to that in the previous work. It does not directly access the user's data in the pages. For example, for page movement within the memory, the operating system will call the TCP to move the pages on behalf of the operating system. And the TCP will encrypt the pages only when necessary. For example, like I/O and swapping. This approach will allow the operating system to continue management without directly accessing the sensitive data in the user's pages. Yes. So, on the other hand, to support the semantic access, we provide a universal mechanism, namely a lightweight capability system, to regulate operating system semantic access. That is, we trap every system call and exception into the TCP to create the capabilities accordingly. Whenever the operating system requires semantic access, it copies the data, actually it copies the data between the user space and the kernel space with the low-level kernel function like copy from user. We mediate such a low-level narrow interface to get the TCP involved. That means whenever the kernel call copy from user, it exactly involves the TCP to check the capabilities before it copies the objects on behalf of the operating system. So that's the first key design components of Blindfold, how we support the user space access by the operating system. As for the second key design components, there's to enforce all the access policies in Blindfold. Our isolation mechanism is the key. And previous work always typically leverages the nested virtualization or the nested paging for the isolation. There is the TCP will manage and switch between multiple nested page tables, and it operator will increase the TCP size and require nested paging. Blindfold employs mediation to page table update from the operating system and switch between them. To be more precise, we enforce all the page table to be read-only for the operating system. That means operating system can no longer update the page table, but when it needs to really update the page table, it will make a system call to the TCP. In implementation, we mediate the implementation of the setPTE function. And in this case, the TCP will be invoked in every page table update. So it also implies that the page tables are out of the TCP, but the TCP can keep monitoring the entire virtual to physical mapping in this way. And there are a few advantages of this design. First, we keep the TCP small because the TCP just keep an eye on the page table update, but not actually managing the memory. And second, this design is more portable to all popular architectures because it only requires a higher privilege level and the MMU, but does not require any other hardware feature like the nested paging. Okay, so so far from the design of the Blindfold, we can tell it introduced overhead only related to the user memory access and in-system call. In the following, we present part of our evaluation results related to these two modules. All the evaluation results are conducted on the Raspberry Pi 4 Module B. For other details, please refer to our papers. And first, our design tries to avoid overhead in the most common cases. there is the memory accessed by the application itself. The memory throughput errand bench shows that our design has little overhead in such common cases, no matter for the sensitive or non-sensitive, applications. However, since we have to trap all page table update into the TCB, we introduce 10 to 20% overhead to memory-intense application like Redis, because the Redis will trigger memory paging very frequently. And beyond that, for I/O-intensive application like Nginx, we typically have even higher overhead, mainly because it involves a large number of system core, which typically introduce about 18% overhead in semantic access. So to summarize, we shows that traditional operating system like Linux is not trustworthy, and we classify all the user space access into two categories. There are semantic and non-semantic access. Blindfold presents a general capability system to regulate operating system semantic access. It uses page table mediation and switching to allow the operating system to continue management without lowering its exact value. That's all. Thank you.
Thank you for the talk. Are there any questions? Yes, I see this is the case. Yeah.
Hello, thank you for the talk. I really love this topic. I had a bunch of questions though. What is this privilege isolation? Because you mentioned there's a higher privilege layer. What exactly is this?
Actually, that's provided by the hardware. Like my prototype is on the ARM VAA, right? So actually, beyond the user's mode, kernel mode, it also provides like the monitor mode, the EL3. So our TCB, actually we call that Guardian. Guardian that run on the high privilege mode, there is actually the EL3. Does this answer questions?
Okay, so you basically take the page tables and you make every update to the page tables from the EL3.
Yes, yes.
So there's a monitor call for every page table update.
Yes.
Okay, interesting. Have you read a paper called the nested kernel?
Yes,
from
I know that.
2015,
I know that. Yes.
Right? I think that idea is pretty similar to this, where the updates are, but the advantage of that approach is you don't actually need a new layer. So what do you think would be the advantage of using the EL3 over something like intra-kernel privilege isolation, which can basically do the same thing?
I think it is a very good question, and actually our paper cites nested kernel. But first I would like to highlight that we may share some similar technique, like we rely on higher privilege level software, but we have very different goal. Nested kernel is trying to protect the kernel, but here we completely do not trust the kernel, right? And nested kernel, of course, it also have advantages. It does not require the hardware to provide a higher privilege level, but we do, right? And as for the comparison between them, actually, for us, actually, the trapping into the EL3 has the high overhead. We didn't show that here, but it does. And for the nested kernel, they do not, because you can consider they are in the same hardware privilege level. So there's just somehow like a function call, right? But I still try to highlight that our design is portable, and I suppose, and I believe our design should be able to implement on x86 with the same architecture of nested kernel. So here, when we say we need a higher privilege level, it can be provided by hardware or the software solution, like nested kernel. Does this answer your questions?
Yep, thank you so much.
All right, thank you for answering the questions. And also let's thank Tsaiwa again for the great presentation.